All right, I want to start by talking about carbon. In fact, I'm going to talk about carbon a lot today because it's sort of central to the climate change story. And oftentimes, when one starts to talk about carbon and carbon dioxide and its role in climate change, we show sort of the sterile but exciting scientific graph of how carbon dioxide concentration is changing over time. And that's sort of what I'm going to do, but it's going to be my spin on it. So let me explain what you're looking at here. This is my great-great-great-grandmother, and the number at the bottom, 1820, is the year she was born, and the number at the top is the concentration of carbon dioxide in the atmosphere when she was born. So I'm talking about carbon dioxide because that's the sort of the main greenhouse gas that human activities are influencing. So when she was born in 1820, CO2 concentration, carbon dioxide concentration was 284 parts per million. When my great-great-grandfather came along a generation later, CO2 was still 284 parts per million. And in fact, you can go back to the previous 10,000 years. We can look at ice cores and measure carbon dioxide concentration. And the concentration never varied much from that 284 parts per million. If you go back 10,000 years, there were about 1 million people on Earth. Now there are 7.4 billion. So over this 10,000 year period where there wasn't much variation in carbon dioxide concentration, we went from 1 million to 7.4 billion. All right, this is now, let's see, my great-grandfather, 1783 birthday. Maybe things are ticking up a little bit, but if somebody had been measuring it and looking closely at that time, it certainly wouldn't have gathered any attention. And I'll just sort of tick along quickly. Grandfather, my mother, me, and then my son. And then we start jumping. And as of today, or as of yesterday, we're at 405 parts per million. So you can see these sort of first 3 generations, or the first 10,000 years, essentially no change. Then we were going up the next 3 generations, ending at, let's say, me, we were going up at around 3 parts per million per decade. Then we jumped to 15 parts per million per decade, and now we're over 20 parts per million decade increase. So the big question is, what happens moving forward? Part of the answer to that is whether we rapidly transition to renewable energy sources like wind and solar and other things, or do we continue to get most of our energy from fossil fuels, from coal, from oil, and natural gas? It also depends on how we treat Earth's ecosystems, Earth's forests, Earth's vegetation. So this is a shot of the Amazon forest, which this canopy, these forests which contain massive amounts of carbon. This scene would go on for hundreds and hundreds of miles in its natural state, but we were in a small airplane when this photo was taken, and just a few miles away you see this. So a single tree in the middle of the agricultural field where soy is being grown to feed, gets shipped to Europe or China to feed animals for us to eat. And I'm often asked, so I should also point out that 3 years before this photo was taken, this landscape looked just like this. So this is rapid transition happening in places. And the reason there's 1 tree left in this field is because it's a Brazil nut tree, which is protected. So you take everything, but you have to leave the Brazil nut tree. All right, the future trajectory of climate change, of carbon dioxide concentration in the atmosphere, also depends on what happens below our feet. So I think a lot, and we think a lot at the Woods Hole Research Center, about permafrost, so frozen ground in the Arctic and all the carbon locked up in that, and what's going to happen as it starts to thaw and that carbon's released. But it also is relevant for soils around here, or soils in the tropics. They contain, as I'll say in a few minutes, lots of carbon. So that's also a big part of the story. All right, Rich Delaney mentioned the Paris Climate Accord. There was lots of discussion there about this 2 degrees C threshold, or the imperative to avoid having the Earth on average warm greater than 2 degrees C if we're to avoid the worst consequences of climate change. In fact, there was a lot of discussion that 2 degrees C is too high, and maybe the target of the threshold should be 1.5. But for the numbers I'll show now, the math I'll show, it'll be for what we need to do to stay below, to have a good chance of staying below 2 degrees C warming. So how much carbon can we emit globally if we're to stay below 2 degrees C? And the numbers I'll show are in billion tons of carbon. it's around, best estimate, 790 billion tons of carbon. So that seems like an awful lot. That's since the start of the pre-industrial period, so 1850, let's say. And the bad news is we've already emitted about 570 billion tons. So you do the simple math, and we have about 220 billion tons to go if we're to stay below that 2 degrees C threshold. So how much carbon is in various pools on Earth or in the ground that is vulnerable to being released? So in fossil fuels left in the ground, again, coal, oil, and natural gas, they're around 1,200 billion tons. In soils, around 1,500 billion tons. This is unfrozen soils. Permafrost, frozen soils in the Arctic, also about 1,500 billion tons. And all the vegetation, forests on Earth, around 500 billion tons. So, the take-home message here is that there's an awful lot of carbon in vulnerable pools that could end up in the atmosphere. Any one of these could swamp sort of our remaining carbon budget if we're to stay below that 2 degrees C threshold. All right, how much carbon is currently being emitted from these different pools each year? So fossil fuels, human activities are putting about 9 to 10 billion tons of carbon into the atmosphere each year from burning fossil fuels. And remember, we have 220 billion tons to go. Soils, around 500 million ton right now. Permafrost, so this seems like really good news. I say zero, and it is in a sense good news, but if you have a longer term perspective over the last many thousands and thousands of years, that arrow went the other direction. Permafrost was accumulating carbon. Now we're roughly in balance, but as the Earth is warming and the Arctic's warming even more, it's tipping the other direction. So the concern is how quickly will this arrow become positive, and how much carbon will be released from permafrost. And finally, forests currently, deforestation and so on, are emitting around 1.5 billion tons per year. So I quickly want to just point out a distinction between soils and forests relative to fossil fuels and permafrost. So sort of on human relevant timescales, fossil fuel combustion and permafrost are really one-way arrows, but there's the potential for soils and forests to manage wisely and turn those arrows around and actually pull carbon out of the atmosphere. And I'll say a few more words about that later. All right, this is a little bit of a complicated figure to describe, so I'll take a few minutes, but this is showing scenarios that we could follow, or a scenario that we could follow over the remainder of the century to stay below that 2 degrees C threshold. So the red line is, and the y-axis, the vertical axis is total greenhouse gas emissions in carbon dioxide equivalent. So you can see there's carbon dioxide, there's also methane and nitrous oxide, other gases that are converted to sort of carbon dioxide, so we can look at them all at once. The red line is sort of a business as usual scenario, and the blue line that says below 2 degrees C is a trajectory that we would need to follow to stay below 2 degrees C. So there's the conventional approaches for reducing carbon emissions, and I'll talk a little bit about that. But an important point that we'll come back to is not only do you have to stop putting as much carbon into the atmosphere rapidly, you also need to start to actively remove it from the atmosphere pretty soon if we're to stay below that 2 degrees C. So I just want to quickly talk about these conventional approaches. So that's renewable energy, wind and solar and so on. And if you look at it one way, so this is global renewable energy consumption and production starting in 1965 to the present. And this is I'd say this at first glance looks like a really optimistic picture. We go from very little to what looks like an awful lot. We're headed in the right direction. But looked at another way, if you compare sort of the renewable energy production to other sources, I don't know if everyone can kind of see this from where we're sitting, but it is, I think it's coal, oil, and natural gas are the big ones at the bottom, and those renewable sources that I just showed in the previous picture, the little sliver of yellow at the very top. So the rate of increase is great, but the absolute magnitude of renewable energy production on a global scale is very small compared to our consumption of fossil fuel sources primarily. So what that previous figure showed is that over the next 50, 60, 70 years, we need to rapidly decline, and let me see if I have a pointer here, you know, these fossil fuel sources need to rapidly drop at the same time as renewable production needs to rapidly increase. So we have our work cut out for us to achieve that. The second thing, as I already mentioned, you know, not only do we quickly need to get off of fossil fuels and reduce emissions from fossil fuels, but in order to stay below that 2 degrees C, we need to actively start pulling carbon out of the atmosphere. There are some fossil fuel emissions that are probably going to be impossible to get rid of in the next decades or in the remainder of the century. So these remaining emissions are from sources that are just, let's say, too costly to get off of. It probably won't be feasible to go to no fossil fuel use in the remainder of this century. But to stay on this below 2 degrees C trajectory, we need to start actively pulling some carbon out of the atmosphere. So there are lots of different ways that people can imagine doing that. This figure just sort of summarizes some, and the sort of the broad categories are at what they label natural mechanisms. So that's managing Earth's ecosystems, whether it's regrowing forests, planting trees where they previously weren't, figuring out ways to sequester carbon in soils through agriculture or so on, a bunch of sort of ecosystem-based approaches, and then the other side is technological approaches. These are things that largely don't exist right now, but at least not on large scales that are economically feasible, but approaches where we could potentially, through technological means, just suck carbon out of the atmosphere or store it underground. We fertilize, lots of different technological approaches, and then in between they have this sort of combination, and this would be approaches where you might use biomass to generate energy and then capture that CO2 and bury it. Again, none of these things kind of exist on scales that can make a big dent right now. We could hope for them to become feasible in the future. Maybe they will, but it'd be dangerous to bank on it. What we do know that we can do now is manage Earth's ecosystems to store carbon. And that's really where a lot of the Woods Hole Research Center's work is focused. We do a lot of work with remote sensing, using satellites to evaluate carbon content of Earth's biomass. So this is just a map that was recently produced summarizing some of our work, and this is actually showing vegetation biomass globally. And the kind of cool thing that we can do now is we can look at this on an annual basis. So we can see parts of the world where they're accumulating carbon in vegetation, where they're losing carbon, and this becomes very relevant in terms of the implementation of the Paris Climate Accords, because lots of countries have made commitments that to meet their commitments, they'll store X amount of carbon within their boundaries in their forests and so on. And what you need is some independent approach for verifying that. So sort of the satellite techniques that we've been involved in developing can now do that on a global scale, on a large regional scale, and on a more local scale. We can come back to that. All right, so just quickly kind of summarizing this part of it, staying below 2 degrees C means we've got to get off of fossil fuels in a hurry. If we don't do that, everything else doesn't really matter. That's number one. To do it, we can think about conservation. Certainly that's got to be part of the puzzle. We need to sort of massively increase the production of renewable energy. You know, we're on the trajectory looks good right now, but we've got to ramp it up in a hurry. And then we need to think about how to switch fuels where we can. So, for example, and for that we need to electrify everything possible. You know, we need that's absolutely central to getting off of fossil fuels, being able to switch to renewable electrical sources, I think. And finally, we need to do all of that, and we need to figure out ways to actively pull carbon out of the atmosphere, either through managing Earth's ecosystems, Earth's forests, and potentially from technological approaches to achieving that. All right, I'm going to shift my focus now a little bit closer to home, either Cape Cod or perhaps Massachusetts. This is just a figure of renewable energy production in Massachusetts. I didn't have it for the Cape, but in Massachusetts starting in 2003 up until, I don't know, 2015, I think. And you can see the same kind of trajectory. The trajectory looks really good, but it's still a relatively small part of our energy use on the Cape. This figure shows sort of a breakdown of the different sectors that accounting for our energy use. It's commercial, residential, transportation and industrial. The commercial, residential, and transportation are each roughly equivalent at 30% or so of our energy use. Industrial in Massachusetts is a bit smaller. And I just want to present a couple of, let's say, case studies or examples of some of those sectors. So the first I'm going to talk about is the commercial, and as an example of the commercial, I'm sure many of you have examples of that, and we'll talk about it later today. I'm going to focus on where I work. So this is a aerial shot of the Woods Hole Research Center. The original building was built turn of the last century, around 1900, and when the Woods Hole Research Center bought it 15 or 20 years ago, we gutted and renovated that and added this, and subsequently we have another building over here. But the sort of whole renovation was designed around figuring out how to minimize the use of energy in the building, and then producing energy in various ways to meet our energy needs. So both through solar and through wind. And we produced just as much as we planned on producing, but the fact is our energy consumption went up. It was greater than we anticipated, both because we purchased another building and also because our computer resources kept increasing, so we could do the sort of climate modeling that we need to do our science, so that we haven't been carbon neutral until now. But we've been thinking very hard about how to two things. Again, it's always conservation or use less, and we're implementing some ways of using less energy, and that's focused largely on how we get our computing done, but we're also producing more. So this is a photo I took yesterday. If you notice in this photo from a year ago, this is just a big field. If you go there right now, that field has a big solar panel. So we're using less and producing more. So in the future, I expect, if I was giving this talk a year from now, I could say on an annual basis we're carbon neutral. Everything is run by electricity on this campus, and yes, we think we'll be carbon neutral in the operation of the campus. All right, I want to now talk a little bit about an example on the residential side, and this is really going to be closer to home because this is my home, which the house was built in 1870. I bought it in 2000. This is what it sort of looked like in 2000. There was essentially no insulation in this house. It was heated by oil when I bought it. We pretty quickly transitioned at that point to gas heat, a high efficiency gas heat. And it's interesting, I mentioned fuel switching earlier, and we kind of, I thought about the fuels that had powered this house at various times. So it started off with wood, as a wood stove. There was evidence that a bit later it was coal. When I got it, it was oil. And then we transitioned to natural gas. So this is where things were as of, 18 years ago or whenever it was, 15, 16 years ago when we made that switch. A few years later, we did kind of a remodeling of the house, which, number one, we got it insulated. Number two, new windows, so we kind of tightened the whole thing up using less energy. Next step in the progression were these solar thermal panels. So we had our hot water was actually electric, so we were offsetting a good part of that by the solar thermal. We then went the other direction in that this is the original part of the house. We did an addition, so we got bigger. But in that process of going bigger, we not only completely redid the insulation. Well, we did really thick walls and good insulation in the new part, but we also got rid of the blow-in insulation that actually didn't do a very good job in the old part of the house, and the whole house got this isoline foam insulation, so the whole house tightened up. So our energy use didn't actually go up very much with the addition. This is kind of a back and forth, good news, bad news, right? So this is like 3 years ago now. We put in this these mini split heat pump system for air conditioning, increasing our energy use. A little bit, it doesn't show up so well here. This is just over a year ago. Next to our solar thermal, we got photovoltaics. So there's some here, there's some on the other side of the house. So and we paid some extra to get some really good energy monitoring of that. And so this is just showing energy production and consumption over the last year. And the sort of bottom line is that over the last year, we used sort of just under 7 megawatt hours of electricity. We produced 8.6. So we have a bit of excess, which is getting me back here and thinking about this transition. So not only does this, I mean, we got this thing really to cool things and make it comfortable, but it also heats. So my kind of experiment over the winter will be to see how much of the natural gas, which we use for heat, I can offset by heating our house with this heat pump using the solar electric that we produce. Now, if I had vision from the very start, I could have done this far more efficiently, but this is sort of, you know, the way life often unfolds, and you take it in steps. I think it's 2 steps forward and 1 step back in this case. And just very briefly, a little bit about the transportation sector. This is just a shot from the Woods Hole Research Center. I think we put in our first electric charging station maybe 3 years ago. Now we're up to, I think it's 4 or 5. And so it's, I mean, I just love, and I don't yet have an electric vehicle, but I love going there and seeing the vehicles plugged in and seeing the wind turbine spinning away and thinking about sort of that connection. And I see I'm getting waved at. Does that mean 5 minutes? All right. All right. And you'll have lots more opportunities in the breakout sessions to hear about success stories that focus on transportation on the Cape and Islands. And finally, we can think about land management or ways of removing carbon using ecosystems of the Cape, similarly to the way we kind of think about this a lot at the Woods Hole Research Center on global or large regional scales. We can think about it on the Cape. And if you think about a many 100-year history of vegetation, forests on the Cape, it's kind of going like this, right? If you were here 1,000 years ago, it's probably forests everywhere. The pictures I've seen of the Cape, say 120 years ago, there's at least, you don't see a tree anywhere. So let's say over the last 120 years, we've been accumulating carbon in Earth's forests. In the last 15 years, I'm not sure. I suspect it's going the other direction. We have satellite records that can go back 15 or 20 years. This is an analysis that we can do to see sort of the recent trajectory. But what's important for the future and for thinking about, you know, a net zero goal on the Cape moving forward is, you know, is the land side going to help or hurt us? What can we do to help pull carbon out of the atmosphere into the vegetation or into the soils or into the wetlands on the Cape to help us achieve that net zero goal? And that's an exciting science, I think, to be done there. So kind of the bottom line on all of this, and this first point I'll make is probably the most obvious, and you all wouldn't be here if you didn't know this. This is really urgent. But like Rich was saying, based on his experience in the Paris negotiations, and I was there. I mean, I think about this stuff every day, but sometimes it hits me like, oh my God, you know, we've been talking about this and thinking about it for a while, but there's not that much more time for talking about it. Particularly, you know, if we're going to achieve this goal of staying below 2 degrees C and not have things get really, really bad. So we've really got to get to work. And it requires rapid progress on a global scale. And the combination of these things can sometimes just be daunting, and it can lead to paralysis. You know, what can I do? How can we get there? And so for me, it's just incredibly exciting to have this group here today to think about what we can do at home on the Cape, in this remarkable place that we live, as a step towards these broader global goals. And the possibility of the Cape actually being a shining example that others will follow is really energizing and exciting. So thank you.